Today, we are very happy to have Simon Caron-Huot from Gill University telling us about holographic cameras. Over to you, Simon.
Yeah, hello everyone. It's a pleasure to be with you a bit virtually. I'm working from home today because I have a little cold. Hopefully my voice will make it through the hour. So I will be speaking about work from this fall. Maybe before I discuss the motivation more broadly, maybe I can give a kind of executive summary. So the object we'll be looking at are correlation function of 4 local operators in an arbitrary quantum state of a theory, not necessarily the vacuum. And the main message would be that these objects, they correspond in theories that are holographic, theories in state that are holographic, they correspond very nicely to scattering amplitudes at the edge of a certain region, and that this information reveals the bulk geometry very straightforwardly when it exists. So the goal is to somehow understand the bulk geometry from these objects. 4-point correlators.
So by scattering amplitude near the edge of the bulk causal wedge, do you mean that you have bulk point singularities, or do you see bulk point singularities in this?
Yes.
Oh, I see.
Yes, that's effectively that. Yeah. So yeah. Feel free to ask to interrupt and ask questions. Yeah. So yeah, we'll start with some motivation. Then we'll discuss exactly some techniques we can use to calculate these 4-point functions in either in holography or in strongly coupled field theories. And then I would give some images of what you actually see from these correlation functions. Give some lot of examples. So we'll start with some broad motivation just to set the context. So the general context is about the gauge gravity correspondence, or more generally, when you have a certain strongly interacting quantum field theories are known to be dual to, in the sense of better described as theories of gravity in one more dimension. That's a famous correspondence. And for example, if you have a theory at a finite temperature, on the left, you put the system at finite temperature, and it turns out that the bulk description in the extra dimension involves a black hole, and then the temperature of that black hole is the arcing temperature of the plasma is the arcing temperature of the black hole, and so on. So there's a lot of items in this dictionary are well understood, and what we try to clarify today is how to think about the geometry of the bulk from the viewpoint of things we can measure on the boundary. Okay, so we're not the first people to think about this problem. So there's actually a lot of ideas that go along the name of reconstruction that achieve this. What we do is a bit different. So I want to explain exactly in what way to be different. So typically, the method that exists to construct the bulk fields from boundary data look as follow. So there's a general idea that the graviton in the bulk is dual to the stress energy tensor in the boundary. And actually, if you know the expectation value of the such tensor in a holographic state, you can plug into Einstein equation, solve it order by order in the radius, and get a bulk metric. So in some sense, with Einstein equation, you can go from one to the other. And similarly, using other bulk equation of motion, you can reconstruct other fields. Now, there are connections with geometry that are well understood. Like if you take 2-point function of heavy operators, typically give you the at space-like separation, they typically give you some exponentially smaller signal, and the exponent is proportional to the length of a geodesic in the bulk, which is very geometrical. And also entanglement entropy is related to area of minimal surfaces. Now, out of these approaches, in my view, there's one thing that's a bit not optimal about them, is that they all involve solving some complicated inverse problems. And you have to know the bulk equation of motion really to be able to do it. And it's really decoding the bulk, right? Someone is doing the experiment, measuring all this 1-point function, and then you use this as your condition to solve equation. So there's basic questions that this raises, which is that, well, if a system cares to be holographic, means that you start with a boundary system, it has some Hamiltonian, and somehow this system encodes a bulk dual. Why should this dual be hidden from us? Why should we have to do decoding? Can't the system decode it for us? That's the basic question we try to answer, and we find that, yeah, in some sense, by using the system, the boundary system, the Hamiltonian, we can also essentially decode the bulk. Something that's more like measuring the bulk than computing it. Yeah. So in terms of broader motivation, so it's all just sort of the big picture idea, not what we like to do, but one of the promises of the DSCFT is that it defines theory of gravity. Like on the one hand, if you're interested in gravity, one of the promises is that CFT is better defined than the field theory side is better defined. So you like to use it to say things about gravity when you're not sure what to do on the gravity side. So an approach which is based on the bulk equation of motion is not ideal for that. Also, from the other viewpoint, one of the promises is that we might be able to say things about specific quantum field theory. And many of the specific theories we're interested in don't have a clear bulk dual. Just to give a precise example here, if we think about QCD at high energies, short distances is a weakly coupled quantum field theory. So its dual will have to be strongly coupled gravity, and we don't really understand that. So it's not very clear in what sense it has a bulk dual. But it would be nice to have an experiment, right? So at least formulate maybe at least a tough experiment that we could do in QCD that will tell us if there's a bulk geometry and okay, to what what is the bulk geometry, and if to what extent it's ambiguous. It'd be nice to be able to answer this question by doing experiment in QCD. So that's sort of spirit we have here, in order to be able to apply these ideas to specific field theories. Something that we have in mind as motivation also is the fact that it's important to understand the local physics in the bulk. So there are a lot of kinematic aspects that are in ADS-CFT, like the fact that the extra dimension corresponds loosely to the size of objects. But what happens in theories that have gravity in the bulk as we know it, that have really local gravity in the bulk, is that you can actually have point-like objects in the bulk that are really localized, not just within plus minus ADS radius distance, but they are very point-like objects. And this is supposed to happen in theories with theories that satisfy these general criteria. And the higher spin gap is essentially controlling the mass of effectively, for example, string states in the bulk, where you no longer have a local description. So this story is now something that we understand rather well for 4-point function of stress tensor in the vacuum of a CFT. We understand, for example, that in a theory with these two properties, this 4-point function cannot differ significantly from the prediction of Einstein's theory. It cannot. We have rigorous bounds on the departure. I will be happy to discuss this more after you want, but we now have rigorous bounds on just as from these two assumptions alone, we can sort of bootstrap this correlator and show that the bulk theory has to be close to Einstein's theory. So looking at simple object like 4-point function in an excited state seems like a natural next step if we're going to understand things like the geometry, not of the vacuum, but the geometry of and the dynamics of say, around a plasma. So that's our general motivation. Today, we won't really do that, but we'll just explore what we can measure from this 4-point function, and now it tells us about the geometry. Questions on these motivations? Okay. So now I describe exactly what 4-point function will look at. So the first basic idea, okay, we start with some arbitrary state of a quantum field theory, and we're going to excite it. We're going to try to we want to have something that's loosely speaking a point-like excitation in the bulk. So we're going to excite it with a high frequency operator. Operator could be simple, like a stress tensor or current, but we inject a large momentum into it. For example, by integrating against a Gaussian wave packet. So we have an operator with a large momentum. If the momentum were close to a light cone, it would create something like some kind of jet of energy in the field theory. But the idea is to not do that and use an operator that's very time-like. Use a momentum that's very time-like. So this creates energy. The energy has to go somewhere, and effectively it would go into the bulk. So let's look at this excited state, and let's ask a simple question. What is the energy density in that state? Okay. And we'll study what correlator answers that question. So just asking that question is a bit like a quantum mechanics problem. So you have a state, you have a measurement, just you have a ket, you have a bra, and you sandwich your measurement between them. So it's going to be answered by something that's like a 3-point function in this type, or is a bracket too much here. So we have this, yeah, so the expectation value in this excited state is some operator like this. Yeah, it's integrated over 2 wave packets. Just here's a quick technical comment. You can basically ignore this, but quick technical comment is that in practice, you don't really need 2 wave packets. Just a wave packet with respect to the distance between those two guys is enough. So we'll simplify the formula in this way. But the main thing to notice about this formula is the operator ordering. When you take the expectation value in the state O psi, you need to put O psi in the bra and the ket, and you put T in the middle. It's very important that the O's are not next to each other. Okay. So the operator ordering will be important in what follows. Yeah. So let's describe that a little bit more. So one way to compute this schematically using a pattern integral is that you have to insert this state O psi, then you time evolve it forward up to the time where you measured your energy momentum density. And after that, you evolve it backward up to this O, which is like the annihilation operator on the left. And then maybe you keep evolving backward up to the time where you define your state psi. So you have to do a pattern integral like this. And we'll be interested in limits in a regime where delta x is small. So these two operators on the left are inserted close to each other. So we already have a picture that looks like on the right. So it will be useful to introduce some, so here I'm kind of introducing some notation in the picture on the right that helps us follow this sort of Schwinger-Keldysh contour in the bulk. So what you should have in mind is that, yeah, well, and then the equivalent way of saying this is that the excitation goes from x to y, and then backward up to x plus delta x on this time fold. Okay, and the bulk picture that I draw like this, you should imagine that it's actually happening in a folded geometry. So I imagine you extend this fold into the bulk. So the geometry forwards in. So the geometry is a representation of the evolution operator, and you evolve, and then you fall back. You go back to your original point. So that's what this picture means. So, and the particle on the blue line just follows this folded geometry. And sort of a nice feature of this limit is that there is actually a singularity as delta x go to 0. There is a short distance singularity, but it's not captured by a straightforward OPE, operator product expansion, like if they were on the same sheet. If the two O's were really next to each other on this contour, then you could replace them by a local operator. But what happens here is that when they become close to each other but on different sheet, they have to create a particle that goes back and forth the time fold. Okay. And as the distance goes to 0, then the energy of that excitation becomes larger. That's what happened. But it's this operator product really creates non-local operators which represent particles moving. So that's just formalism. So what does this energy density actually look like? So well, this was answered by these people several years ago, and And essentially, this operator here follows some null geodesic in the bulk. And we can control the shooting direction very precisely from the momentum that's conjugate to delta x. But what we see in the boundary is that as this point particle goes deeper and deeper into the bulk, we just see by the radial correspondence, it's supposed to look larger and larger in the boundary and actually looks like an expanding shell of energy. So with this technique, it's possible to, as was understood long ago, with this technique, it's possible to create a very high quality point excitation in the bulk. But then all you see in the boundary is just a shell of energy, and there's no hint that it's actually like a point particle. It's like a shell. So in some sense, we're creating a very, we have a very fancy cannon, but we're looking at it with a crappy camera. Okay? So now we'll try to improve the camera. This is basically what I just said. So there have been two variants of the camera. One is a bit more intuitive, and the other is mathematically simpler. So you pick which one you prefer. I will introduce, and the point of them is to really measure the bulk geometry in which this particle evolves. Maybe I should step back here and say one thing. So this sort of experiment you can do even if the bulk is not in a vacuum state. And by injecting a definite momentum conjugate to delta x, you can really tune very precisely the direction in which you shoot. So in some sense, you control the tangent vector, initial condition of this geodesic near the boundary. But when it goes in the bulk, if the bulk is curved, then it will follow some like null geodesic that's all curved. Okay? But you have control over you don't know where the particle ends, but you have perfect control on how it starts. We can do this even in a curved geometry. So now let me describe the camera. Well, the camera is actually, we have this bulk and we have a 2-point function on it. That's something like a radar. It's like we send a pulse and we record its reflection. Like a 2-point function in that excited state, which really is a 4-point function because you need to create the excitation, absorb the excitation on the left, and then do your radar measurement in the middle. So it's a 4-point function. A good analogy to this is something like the Pioneer spacecraft that we threw into outer space, and by bouncing light off it, we measure the geometry of the solar system. So the same idea here. So it's a very simple idea. We launch this probe that's like a point particle into the bulk, and then we bounce some light off it. Okay. In the ideal regime, where the light that we bounce is controlled by geometric optics, then to visualize this measurement, you have to think about 3 null geodesics. So the null geodesic that start from Z. So the idea is that, so what are we looking for in terms of signal? So you create this bulk excitation at X, create this pulse at Z, and generically, if they're space-like separated, there'll be one point where they intersect, point P, and then there'll be a sharp reflection, something like a bulk point singularity, as the point Y approach the future light cone of the point P. So there's a whole kind of hyperboloid on the boundary along which is a singularity. Technically, how we're going to calculate this object would be very similar to so-called bulk point singularities was analyzed in these papers. In fact, the only thing we changed is the operator ordering. That's the only change compared to this paper. But the operator ordering completely changed the experiment, because in this previous experiment, the blue particle, you needed effectively to work in global ADS, and you needed to recover the blue particle somewhere in the future. It was like you had 2 in states, 2 out states. So here, all we've done is change the operator ordering, but that completely changed the interpretation of the measurement. And now, for example, this blue particle, as far as we care, it could fall into a black hole. Like we don't need, it's like for the Pioneer experiment, you don't need to recover the spacecraft to get a measurement, right? You just bounce light off it. So it's a completely different experiment than experiments in which you try to recover the probe. Yeah. So that's the main novelty here. It's all due to the change in operator ordering. And you can tune the shooting angle of this object, and you can imagine using it as a camera as follows. So
in the original paper, the Maldacena, Simon, Staffin, and Zhibodov, there was a momentum conservation condition which one recovers because of the specific ordering of these operators. So do you still recover that? Like,
well,
or maybe
yes. So this picture still conserves momentum, but now it's not. It doesn't really. In their paper, this really forced them to effectively use global ADS. So you have to shoot. Yeah, you needed to have something in the back of X. But here, the way to preserve momentum is that you evolve in this particle here as like positive energy, but it's like negative energy propagating backward.
I see.
Just by changing so instead of having, so it's the same momentum, but instead of evolving forward in time, now to evolve it backward in time. So the momentum is still conserved at this interaction point, but that no longer gives a constraint on the geometry of the experiment. And we're going to see this in examples. So now let me describe something that's going to be a bit simpler to interpret, although it's a bit more abstract. So maybe a bit harder to actually measure, but easier to interpret if you could measure it. So we call it an active camera. An active camera does not exist on the market. There's no analog device. It's based on the out-of-time order correlator, which is harder to measure experimentally. It requires the ability to evolve a system back and forth, back in time. So the way it works is you create this excitation O, evolve it forward in time. You create this excitation O prime at Y, you evolve it backward in time. And effectively, this out-of-time order correlator, in fancy language, it measures how much the excitation from Y interferes with how much the excitation from X interferes with your ability to evolve Y backward in time. So it's a very subtle quantum interference measurement. Now the data is a bit simpler to describe because now we basically have two shooting points, X and Y. And the small differences, delta X and delta Y, are Fourier conjugate to basically the initial conditions of null geodesics. So now this correlation function in the bulk picture, it's a 4-point function on the boundary. And in the bulk, it's like a correlation function involving two null geodesics. And the signal that we'll be looking for is the following. As you tune the angle of this geodesic, as you tune this shooting angle, there'll be a place where they hit each other in the bulk. The bulk impact parameter goes to 0. And there you get this singularity is your signal. Okay. And you can see how you would use it as a camera, loosely speaking. Imagine you try to imagine the path of the particle that's launched from X. Then if you fix the point Y and scan over angles, you're literally taking a photograph of where that particle is at a given time. It's like it's codimension 2 from the bulk perspective, just like a photo camera. It's like a codimension, image. Now, if you do this measurement at different times Y, then you're making a movie of the bulk particle moving. And that's like a 2D movie that we'll call a cinema. But how do you make a 3D movie? Well, there's a simple way. We just put two cameras next to each other, and then you have depth information. So we'll be able to do the same thing with this device. Okay? So you can imagine just by scanning over angles at different times y, you make a movie, and you do this from two different shooting points, and you really get a 3D movie of this blue particle evolving into the bulk. So that's the sense in which this 4-point function images the bulk geometry. It images the path of test particle in the bulk. And you have a few knobs. So you have shooting points, x and y. You have the shooting angles. You can also play with the shooting energy. And you also play with the width of the wave packets. The accuracy that you get actually is limited by the width. So like there's a famous rule of thumb in optics that if you have an object, if you have like an eye, like your eye has a size L, and looking at the wavelength 1/p, then the angular resolution is 1/pl, and the same principle effectively applies here. So if your wave packet is too small in X space, you're not able to resolve angles very accurately. So you have to choose you have to choose all these parameters, and the hope is that by tuning these parameters, you can get a sharp image, meaning a singularity that's very sharp as you approach this bulk impact parameter go to 0. Very sharp singularity is a function of angles. Okay, so that's a signal we'll be looking for. It's important that the bulk has at least 3 space-time dimension, otherwise there's no impact parameter. Yeah. So I will just sketch some of the mathematics that we can use to compute this correlator. One of them is kind of OP that I briefly alluded to before. When we take these operators, we take an expansion as delta x go to 0, but on different time folds of a Schwinger-Keldysh path. And as I mentioned, we get non-local operators, which in holographic theories you can understand as essentially an integral over like-ray of the metric. And it's integrated over angles. So effectively you get the operator is supported on all possible light rays that emanate from X. So this formula at the top will reproduce effectively the leading iconal approximation. So we imagine that this light ray on the left is a source of a graviton, which interacts with the other graviton through a retarded propagator, actually. But this sort of formula actually works even beyond the iconal approximation, so it will allow us to account for string theory effects, where now these quantum numbers here become replaced by Regge trajectories. I would say something a bit more concrete in a second. But one thing which is a bit, maybe the most important thing I should mention here is that none of this technology is new. It was all developed a dozen years ago or so in the context of conformal Regge theory. And it turns out that the same technology applies to this particular problem. So I would like to stress, so this technology is not familiar to most of you, but I would like to stress why these techniques are related to each other more than exactly what the solution is. So the relation goes as follows. Okay? So conformal Regge theory is about looking close to a vacuum state. The picture on the left. And the diamond is, so this is at the surface of, so this is in Minkowski space. This diamond represents Minkowski space with past null infinity and future null infinity here. And you can imagine that this picture lives on the, so this is the boundary picture. So you can also think of it as living on a cylinder, the surface of a cylinder. Okay. So this region is this region of space-time we normally have access to. And the rigid limit is we take an object and we apply, well, we scatter two highly boosted objects against each other. So when we apply a large boost, then our initial operators approach null infinity along some null direction. And the special thing about this limit is that any light ray from 1, if you shoot light ray on 1, it opens up along the cylinder, and all the light rays, all these light rays focus again on point 2. So they're separated by pi on the cylinder. That's a special feature of this limit, and it's known that this limit is controlled by light ray operators that live on this cone. Now, the thing which is surprising about conformal field theories is that there's nothing special about infinity. So what's important about these 4 points is that there are like 4 points on the cylinder, and the only thing that's important is that point 1 and 2 are separated by pi. But you could move the diamond compared to this. You could move these points compared to the diamond, and you still describe the same experiment. In particular, if you move all the points northwest by half a patch, you end up with a configuration like this. And there's also this cool fact that going outside the patch is like folding the picture and going back on the first patch. So these two correlator A and B are equivalent. I just like translated them on a cylinder. Picture B represents a different physical experiment, which is more like the one that Hoffman and Madsen described, where you have a particle decaying from the origin in space-time, 1 and 2. It's creating some state, and we're measuring the state near infinity, doing some measurement along 3 and 4. So that's something that we call detectors in a recent paper. So somehow the physics of what you can measure at infinity in the conformal theory is the same as the physics of what you can scatter against in the Regge limit. They're the same physics, they're just translated by half a Poincaré patch. And similarly, you can go further and translate this picture southwest by half a patch. Now we end up with this. It's a bit hard to follow all the folds, but hopefully I didn't make a mistake in which line is above or below the others. It's now you see that you have something like you have well, this thing requires 4 folds, and it's really out of time order correlator. And this thing describes a kind of scattering process at this particular place where the lines crossed. Yeah. So in the CFT vacuum, all these limits are equivalent to each other, which means that we can calculate this thing without having to yeah. So essentially, you just have to open the results from the old papers, which study the Regge limit, and you get the results for this out of time order correlator. This relation holds in vacuum for CFTs. If you have an excited state or a theory that's not conformal, the limits will still will have a similar structure, but they will involve different coefficients. Okay. So let me also describe a bit how this is related to a bulk scattering amplitude. And maybe it's a bit technical. That's not really necessary. I will go fast on the slide, but yeah, this out of time order correlator, you can think of it as you evolve an excitation forward in time, 1. But the main thing is that a single particle excitation evolves trivially in time. As long as the excitation is stable, which would be the case for highly boosted excitation, the evolution of 1 forward in time is rather trivial. And similarly, the evolution of 3 backward in time is rather trivial. So this process really is a scattering amplitude of 1, 4 going to 2, 3 backward in time, so complex conjugated. So it's easy to see formally why this out of time order correlator, assuming that we're focusing it using suitable wave packets in the bulk, is proportional to that amplitude. And that will be useful for calculation. Yeah.
So suppose that I have some bulk contact term, like let's say, and I want to see how the bulk point singularity emerges from this time ordering. So you will be able to give me some I epsilon prescription for my propagators, I see.
Yeah. Yeah, exactly. That's what I'm describing here. And the decision point, which will simplify this calculation, is that if you look on this picture here, particle 1 evolved forward in time and then backward along this contour. But essentially, this is still a single particle state. And evolving forward and backward in time, a single particle state is trivial. So nothing really interesting happens on the first branch, and nothing happens on the third branch. The scattering really occurs on the second branch. So that's why the epsilons end up not so different. So that's why what you can end up computing is essentially the usual scattering amplitude with all the epsilons flipped. It's flipped because the second branch goes backward in time. So this is minus I epsilon.
2 and 4 still need to be ordered, right? I mean,
yeah, the ordering of 2 and 4 is important, correct. Actually, this is a side comment, but there's something that's fun and you can actually do even in flat space. If you look at old papers from S matrix theory, like from the 50s, before people internalized the LSZ reduction formula, people were thinking about in and out states kind of attentionally, right? You can create and annihilate in states, create and annihilate out states. And so and in this language, it's actually something that what we're doing here is actually something that's very natural. We create an in state, we create a out state, and yeah, so this is something we're further exploring in work in progress. But this is you can do the similar thing also in flat space, and this object turns out to be exactly equal to this complex conjugate scattering amplitude. So this is sort of thing that they proved in the 50s, long time ago. So nobody knows that anymore. But it's kind of fun to see that they were playing with this operator orderings also back then. Okay. And okay, I will skip this. Okay, so then let me show what the images you get actually look like. Do it first for a planar black hole, and then we'll discuss theories where it's not expected to be holographic. Okay. So in the vacuum state in EDS3 CFT2, you can use this formula from conformal Regge theory that I just mentioned from the vacuum, and they give us an answer for this correlator. And it is a plot of what it looks like after if we transform P. Yeah, sorry, I wish I give the formula, but it's not there. So what the formula shows is that, so the angle here, so the left direction is like the bulk. So it's like which direction you see a signal into the bulk. Okay? So this means that the signal is peak around a specific angle, shooting angle P. Actually, just to be completely clear, I've taken 2 derivatives here of the correlator to enhance the singularity. That's not too essential. Okay, so that's why there's singularity. Now, okay, before I proceed, we'll ask you to try to visualize in your head what will happen to this image as I evolve, if I take it at a later time. So suppose I fix a shooting angle from the origin. I increase the time separation. And now I make the image again as a function of the shooting angle. Okay. Try to visualize what image you would get. If someone has not seen this talk before, you can try to say it loud. What will you see? Okay. It's important that everyone can visualize it before we move on. Yeah. So if I change the time separation and I look at the intensity of the signal as I scan over the angle P, where would the peak be at a later time? Yeah, someone said something?
I want to say that like the yellow spot will move up because the shooting from the origin is gonna like the null geodesic will go further into like along the way.
Yes. Yeah. Yeah, maybe the picture is a bit misleading because I drew them as curved, but really in vacuum, these lines are straight. Yeah. So this was a trick question. So the word picture is like a cone, and when you rescale it, the angles don't change. Yeah. So as you go to later time, you just rescale this cone, but the angles don't change. So actually what you see here is the whole movie. This is a fake play button. Okay, right. So in vacuum ADS, you do this experiment and you see that nothing is changing with time. So you're shifting in one direction, and the picture you make in your head, just the cone gets bigger and bigger, but the angles don't change. Okay. So now let's do this in a more interesting state. That's like a black hole. Okay. CFT2 is actually like very easy because you can find a 2-point function in at least a planar black hole just by doing a conformal transformation. And you can actually then you're back to using the results from the flat space-time correlator. So before we show this, oops, we try to discuss. Now we make a fancier image. Yeah, as I mentioned, there's a way to get depth information by looking at two eyes at the same time. Below, we'll find another way of looking at depth information. You can think about it before we get there. But yeah, by looking at a left eye and a right eye that are slightly displaced in space, now you can make this movie. And at initial time, but now when the particle is close to the boundary, then you're looking at it you're very cross-eyed. That's what you see in this picture. And as the particle goes deeper into the bulk, the angular separation between the two images gets smaller and smaller. That's what you see in this thing. And if you were in vacuum, it would keep getting smaller and smaller. Essentially, the angular separation goes like the boundary distance divided by the radial depth. It goes like 1 over depth. Okay, so it would decay, it would keep decreasing. What happens in the black hole is that you see that the angular separation stops changing. So that's a signature that you've hit the horizon. Because in terms of boundary time, you effectively freeze. So you see that you hit the horizon just from that signal. What would be another signature of hitting a horizon? Yeah, so here I've not kept information actually about the intensity of the signal, but that's another thing you can measure. And in fact, the intensity of the signal evolved in time in an interesting way. So explain it a little bit. Naively, you might thought that as you approach the horizon, you get a large redshift factor from getting information out of the horizon. It's not quite what happens. So what happens looks more like this curve on the left. What happens actually, you get a blue shift factor because this is an active camera where you're shooting something, you're actively shooting something backward in time close to the horizon, and it's scattering against something that's a normal excitation is going forward in time. And the center of mass energy in the bulk grows by a blue shift. So that's this factor. So this is this famous exponent that also features in the bound of chaos. So you see this exponential growth with time of the intensity, and the exponent gives you the temperature. Actually, more precisely, it gives you the surface gravity near the horizon, near causal horizon. At early times, the intensity goes like time difference square, and that's a signature of scale invariance. So you know that in this theory, in the UV, you're conformal, and then there's a horizon. So this is what you get if you measure the intensity of a signal as a function of time separation. And the other thing is a parallax that I already discussed, which is how much you move your head to get the change of distance. So that's a proxy for the bulk radial coordinate, and it freezes as you approach the horizon, as a particle approaches the horizon. So these are things you can measure. And what I want to argue now is that if you can measure this, then you effectively measure the bulk metric, really. And the way it works is, okay, it's easiest, of course, in simple states like this one, which is if we assume that the CFT state was like thermal state, so it's translation invariant, you can make a general ansatz for the bulk metric. And then the idea is you can ask what do null geodesics do in that metric. So you can use geometric optics in the bulk to see how the measurements are related to this function A of R and B of R. What is a square? It shouldn't be there. So we can measure, so the intensity is the blue shift factor, which is determined by A and B. The parallax is the shape of null geodesics. It's also related to A and B. So you can see that you can relate this measurement to A and B, and vice versa. You can invert the measurements and express A and B, having the radius in this gauge, in terms of things you can measure. So this is the intensity that I've plotted on the last slide, and the parallax that I've plotted. And actually, you don't need to integrate anything. You just take derivative of this data, and you get the you extract the bulk metric, basically R, A, and B. And then you plot them. And okay, I don't even know how to check this. This is not a way to compute metrics analytically, but you can plot it, and it's exactly the actual solution for a BTZ black hole. Okay? So yeah, so the way you should think about this is that you could ask a colleague or a graduate student to give you this correlator and their favorite metric, and then you can play a game where you can try to reconstruct that metric. And if you know enough correlator in the metric, you'll be able to reconstruct the metric. That's how you should think of this experiment here. Yeah. And yeah, so what I said here, so we see that the data in this out of time order correlator, which are essentially the intensity and the parallax, very literally give you the bulk metric. And it's interesting in this context to ask, like, what do Einstein equations in the bulk imply for the data that you measure on the field theory? And they imply these two equations. So in this symmetrical setup, Einstein equations are two first-order equations, and you express them in terms of these two things you can measure, and they give you those two equations. It would be very, very interesting to be able to derive those from the CFT perspective. So if you know these two equations for all times t, it's equivalent to having Einstein equation for all radius r. So if you could derive this equation, effectively you will have bootstrapped the geometry of a black hole in ABS. I don't know how to do that, but that's nice to understand what this equation means. I find it very surprising that a local differential equation in the bulk implies a local differential equation on the boundary. Is equivalent to a local equation in R in the bulk is equivalent to a local differential equation in time in the boundary. That's a bit surprising.
Where does the assumption that the bulk is weakly coupled come in?
Aha. Yeah, exactly. So those two things should only be able to derive this from the boundary viewpoint when the bulk is weakly coupled. So let me come to that. Okay. So let's try to ask what will happen if we do this experiment when the bulk is not weakly coupled. Okay. You can try to do the experiment. Okay. And well, one thing you can do, for example, if the coupling is strong, you can replace this bulk amplitude by a Virasoro-Shapiro amplitude to account for stringy effects, for example. Something else you could do, you could consider a gauge theory at weak coupling, and then use formula from conformal Regge theory to tell you what the correlator looks like. And okay, I have one more slide about formulas on this. I would just show you the plots and come back to this thing. So what you see looks like this. So this is so the CFT here is 4-dimensional n equals 4 square angles. And as you go to the right, you have stronger coupling in the CFT, which means that the bulk is becoming weakly coupled. But the string length is becoming small compared to the ADS radius. And you see that this bottom right image is what a point particle looks like. Okay, so the blobs here are like the direction. So the picture is that you shot a particle with a moment. Try to shot a particle so that it goes straight into the bulk, and then you measure at later time at which angle you see singularity. So the bottom right picture really looks like you have a point particle in the bulk as a function of angle. As you go up here, this is still working in this regime where the theory is weakly coupled in the bulk, and also the string scale is small in the bulk. The string length is small. But if you use wave packets that are not appropriate, then you have a large uncertainty in your shooting angles, and you also don't get a signal. So as you go toward the left, in the left column, the signal is limited by the bulk dynamics, which is not here on the left, extreme left, they have weakly coupled CFT, so the bulk has nothing to do with holographic theory, and you don't see any nice signal. And the top line, the signal is limited by optics. So like it's like a camera, right? If it's out of focus, you're never going to see anything anyway, even if the dynamics is favorable. Yeah, and the effect of bad optics and the effect of poor bulk dynamics are similar. So if you try to do this, so long story short, you ask, well, why is it important in this experiment that the bulk theory is weakly coupled? Well, if it's not weakly coupled, you'll just see a blur. If you do the experiment here and this is supposed to be the image of a point particle in the bulk, then like you don't know where the point particle is. So the camera doesn't work. It just doesn't work if the theory is weakly coupled. And the CFT is weakly coupled. Yeah. Does that answer your question?
Yeah.
Yeah. And okay, I will kind of give a kind of more formal explanation of this. There's this famous plot of Regge trajectories that these people introduced in conformal theories that really explain, in my opinion, what happens. So these lines are supposed to pass through the operators in the spectrum. So A at spin 2, vertical axis is spin. It's often called Shufalchi plot. It's spin versus mass or scaling dimension. So dimension 4, spin 2, this would be like the stressed answer at this point. And then this line should pass through other local operators in the theory when the spin is integer. In the weakly coupled theory, the other single trace operators that you have, so this curve actually only cares about single trace operator for reasons that I'll be happy to discuss more. If you in the weakly coupled CFT, the operators you have are like fields with more and more derivative, and derivative increase the spin by 1 and dimension by 1, so you get the 45-degree line. So in the weakly coupled field theory, these trajectories are like a 45-degree line, and interestingly, this level crossing here that connects to a nearly horizontal one. But and at strong coupling, what happens is that these operators get lifted to the higher spin operators get lifted to higher dimension. So the correct criterion of having a theory that's holographic is a theory that has a gap of higher spin single trace operators. And when you have such a gap, the trajectory becomes very, very flat. And the sort of experiment I describe tells you why this is important. Having the Regge trajectory very, very flat makes it possible to use large momentum. And the horizontal axis is like the momentum in EDS. So if you want to have access to large momentum, you need to have a very flat trajectory. Otherwise, the modes with different momentum will acquire very different energy dependence and will decohere from each other. So in order to be able to currently superpose modes of all sort of momentum, you need a very flat Regge trajectory, which means that the first higher spin state needs to be very heavy. So this curve that was introduced by them really give a way to explain why. So the curvature of this trajectory is really what control how blurry the image is. And it's kind of fun also. You can do the same experiment in the Ising model. This is my best estimate for what the Regge trajectories of the Ising model are, and then using this trajectory, I could produce this plot. And yeah, if you try to, so if you do your best to create a point-like excitation in the Ising model and see where it is, you shoot it left and you think it's right. You really have no control over its position. So that's one sense in which Ising is not holographic, you could say. And because it's very hard to use hard, you don't have access to large momenta. That's why you cannot see point-like particles in the bulk. So it does not have a local holographic dual, is the precise statement. So yeah, I'm pretty much done. I just wanted to say a few words about the radar camera, because it's a bit simpler, but the geometry is a bit harder to visualize. But here the idea is, so here I've shown so this is, you should think of this picture as a cylinder. The outer boundary is the CFT measurements you can make. And in the bulk here, I've put a black hole. And this experiment is really like, from the point X, you sent a probe and you threw a probe into the bulk. And then from point Z, you throw a pulse that bounces off it. And at point Y, you record the singularity. The singularity as you approach this black hyperboloid on the boundary, that's the reflected pulse. So for fixed Z, there's hyperboloid on Y, along which is singularity. And actually you can, all the information about like the parallax and so on is essentially encoded in the curvature of this. So by analyzing the shape of the singularity, you get to know exactly where the point P is, basically. And then you can change the point Z. One thing that's interesting about this picture is you see there's a lot of redundancy. You could use any point Y along this hyperboloid to probe the same bulk point P. Also use any point Z here, any point X. So there's a lot of redundancy in this picture. And somehow in the theory that's holographic, all these measurements end up controlled by the same bulk geometry. So it's remarkable how much redundancy there is. And yeah, it's not clear whether that's something we can use, but yeah. And also the other thing to stress is that this sort of experiment works even when you approach, even when the probe approaches the horizon of a black hole. So that's the main difference compared to the previous approach, like this bulk point singularity or like cone cuts. But here we don't have to recover the probe. The probe can fall into the black hole. We don't care. We still get the signal. Okay. So done. Yeah. So the main message is that, okay, there's from 4-point correlators, you can easily read off what the bulk metric is in theories where, yeah, and this works in arbitrary state, an arbitrary holographic state. And if the state is not holographic or the theory is not holographic, then okay, this experiment would just give you a blurry image. So you get a metric only when there is one. We haven't done much with it yet. Eventually, we'd like to use this to, was mentioned, to somehow bootstrap the metric from the boundary perspective. But there are a lot of basic questions, even before we get there, like how to get other bulk fields, not just the metric. It's interesting to study more extreme geometries, like clearly this if the bulk geometry is singular or not. Yeah, it's interesting to understand how it breaks down. And yeah, I mentioned bootstrap. Possibly there was nothing particularly crucial about being in asymptotically DS space here. You could do similar things in asymptotically flat space, throw in gravitons and throw in particles, try to do scattering in the background of a black hole, for example. And yeah, clearly the correlator, as I introduced, only allow you to study outside of causal horizons, but maybe there are tricks using modular flow, whatever. Maybe there are tricks that one can use to go beyond that. So, yeah, thank you.
So like in terms of like, suppose I'm thinking in terms of the CFT correlator, and suppose I'm like in some sort of Regge like causal configuration. Usually one doesn't see this bulk point singularities, right? In Regge, like, yeah, I'm a bit confused as to how from this OTOC like.
Yeah, I see what you mean. Yes.
Usually that it involves an analytic continuation.
Yeah. And this analytic continuation is this analytic continuation is there actually. So in this setup, what you would call the normal Regge sheet is when delta x is time-like.
Yes.
Yeah, but it turns out that when you study this Fourier transform, it's actually dominated by delta x space-like. So this transform is using both.
Oh, so somehow there is an analytic continuation involved in this. Yeah. I see. So
yeah, it's a bit non-trivial that these formulas seem to work even when delta x is not time-like. But I agree with you that the regime where, for example, we can bound the out-of-time order correlator, the regime where we have bound of chaos and that sort of constraint is when delta x is time-like. But these formulas seem to work even beyond that.
But there is no way to extend the derivation of chaos bound to this sort of regime, is it?
No, not that I know.
Thank you.
So a quick question on the next slide. I think it's the next one. Can you go with another one? Okay, so you have this, the next one, sorry, one more. Yes, sorry, one before. I think we're a bit out of sync. So is this slide, yeah, this one, where you have this, this is the square there, where you have this correlator trying to calculate, and this corresponds to this out-of-time order path. How do you get from one to the other? It's not super clear to me why they're equivalent. Why these two pictures correspond to each other is not super clear to me.
Okay, yes, the one on the left, the one on the right.
Yeah.
Yeah. So what I'm trying to do here is to fold things as literally as possible. So you can see that the fold between 1 and 2 here represents this folding here. So the picture on the right, let me be clear. Where this folded is actually the whole space-time geometry, not just the paths of particles, but the whole space-time geometry. So on the left, right, to compute the thing on the left, you have to imagine you have 4 copies of space-time, and the path integral glue the fields at the folds, right?
Yep.
So on the right, I attempted to draw these 4 copies of space-time all stacked on top of each other. And the folds describe how the particles propagating, how the particles are glued as they go through the folds.
Oh, okay, I see. All right. Okay, so it's like 1 is in one fold, 2 and 4 in the second fold, and 3 in the third fold.
Exactly.
All right, great. Thank you.
Yeah. And you can see that the place where the lines cross is when they are on the same fold.
Yeah.
And that is basically having 1 and 4 crossing against 2 and 3. That gives this scattering process.
Okay, and since in that fold, 2 comes before 4, then it's the ordering that you have there. Okay.
Yeah. Yeah, the formalism is not so familiar, but the operator ordering is one. So maybe there are, just to summarize the main difference compared to the previous work. Really, the operator ordering is the main difference, and the other gadget is also the Fourier transform to control shooting angles. So, but it's really, compared to earlier work, these are really the two new gadgets. Yeah, so it's important to properly understand the operator orderings.
Sorry. There is also this idea that I'm not sure what's the status of this, but like I definitely remember some statement like that 1 over n corrections resolve the bulk point singularity. Like
Yes.
So like, are you actually proving that, or are you observing? I'm maybe.
Yes. So from the viewpoint of examples, this is already kind of understood how the singularity gets resolved.
Right. But
yeah, exactly. Then the things that are not clear is the extent to which this happens in any theory.
Yeah.
I think here at the very least, stringy corrections make you resolve the singularity in the sense.
Yeah, that's I guess.
Yeah, but also you'd also expect, even if you don't have stringy effects, you will think that in the bulk, as soon as you hit like the Planck energies, you will get macroscopic time delays, and that will also destroy your image. So from the viewpoint of this camera, these effects which resolve the singularities are nuisance.
Mm-hmm.
You want the singularity to be as sharp as possible.
Right.
So if you use, for example, energies are too high, such that the bulk center of mass energy exceeds the Planck length at the scattering point, the Planck size at the scattering point, then you will also blur your signal.
Right.
So yeah, you have to hope that there's a choice of boundary energy such that you need. It's not guaranteed that this camera always works, because you need the center of mass energy at the interaction point to be less than Planck, but to get a sharp angular singularity. But you also need the bulk energy to be large enough that you can trust geometric optics on the way to the scattering point. So yeah, parametrically, if you have a smooth geometry, it will work. But the geometry is not smooth, it may not work.
Any other questions, comments? If not, let's thank Simon again.
Yeah, thank you.
Thank you.
If you want.
Hi.